So as we're studying these real-world polynomial models, we have to make a decision on what kind of model we want. So here are some choices. We could do a linear model, we could do a quadratic model, or a cubic model, or a quartic model. Now if you're using a TI calculator, these are the different ways that you can tell your calculator to create a model. If you're using Desmos, these are the equations you're going to want to put in, referencing your data points. That's what this is doing. It's referencing your data points and coming up with that best line. So depending on what technology you're using, these are your choices. But how do you know which one to look at? When we studied lines, we always looked at something called the correlation coefficient, or the R. But now that we're talking quadratics, cubics, quartics, bigger powers, we have to look at something a little bigger. They have an R squared. These functions all give an R squared. These functions all give an R squared. So here is our first example, and I put a table into Desmos, my X's and my Y's, and I'm looking at the data points, and they're definitely not in a straight line. But if I try the linear one first, if I turn on this linear one, yeah, they don't fit great. And here's that R that we always used to look at. It's a decent line, but maybe not the best line. And you'll notice right above it here is the R squared. So we're already seeing that that R squared is here. So let's try a different one. Let's try the quadratic. Now, if I look at the quadratic example, here's the R squared. It's definitely better than the line, but still not great. So let's go one more step and let's look at the cubic. Now the cubic is looking really good, and I'll turn these other two off so you can see it a little better. But that cubic looks really, really good right now. It's going through every one of our points. And if you look at the R squared is 0.998, which tells me this is a great model for the data points that we have. Now, I'm going to look at the quartic just in case, but we see that the quartic is not nearly as good. It misses one of those points. Our R squared is actually 0.63, so it looks to me like the best choice is going to be the cubic. We've got an R squared of 0.9998. Now, they give me the graph, but they also give me the A, the B, the C, and the D for this model. So I can actually write this cubic. Y equals negative 0.0124x cubed plus 0.433x squared minus 3.29x plus 10.08. I've got all the numbers there. I've got all the points. I could graph this just like they did here in Desmos. So now we're going to take a look at another example using our TI calculator. I already went into the stat menu and I edited my data points. So if you want to put in the same points, you certainly can. Looks like I have 4 points in there. You need to see what they look like on a graph. There they are. But what we want to do is we want to calculate a regression line. So I'm going to start with a linear regression line. Notice it's using list 1, list 2, so I calculate it, and this is what it gives me. Now you'll notice that the R looks really good. 0.98 is almost 1, so this looks like a really good line. And if I look at that R squared, I get 0.96, so it's looking really good. But I'm going to check the other ones just to see. So we go back into the stat menu, and we go to calculate. Now we're going to look at a quadratic regression. Using the same set of data points, and I go calculate, and now my R squared is 0.976. Not as good. I'm still leaning towards that line as being better, even though this one is still pretty good, but not as good as the line was. Let's go back into the stat menu. Let's go over to calculate. Notice there's a cubic, there's a quartic. We're going to check one more. I want to check the cubic, and see if it's any better than that line, because right now the line is looking best. But I go ahead and calculate, and that is something I was really hoping for. My r-squared did get better. I actually got a 1, so it says it can fit these points perfectly, and these are the coefficients to put into this cubic function. So I went ahead and put that cubic function in, and now when I graph, you can see it goes through all of those points just right. So I'm definitely going to choose that cubic function of 1x cubed minus 1x squared plus 2x minus 3 as my choice for this set of data points. But we have something at our disposal that's actually even a little easier to get us in the right mindset. It's called the point principle. Okay, and your book calls it the n+1 point principle. The point principle says for any set of n+1 points in the coordinate plane that pass the vertical line test, there is a unique polynomial of degree at most n that fits the points perfectly. So let me put this into easier language. However many points I have, if I go one less, that's the degree that's going to fit those perfectly, that degree or less. So let's say I have 4 points. So if I have 4 different points in my graph, 4 minus 1 would be 3, so cubic, or less, quadratic or linear. If I have 3 points instead, 3 minus 1 is 2, that's a second degree or a quadratic model. So I would choose this one or the linear one. Once I get past 5, 6, 7 points, it could be any of these, but the point principle narrows it down to what it could be at most. So my final example is using some data from milk production in the United States from various years, and I already entered that data into my table on Desmos. And this number here is actually in billions of pounds. So in 1955 in the United States, they produced 16.5 billion pounds of milk. In 1980, we produced 22.4 billion, and in 2005, we produced 22.9 billion. If I use the point principle, I have 3 points. If I subtract 1, that means the highest I could use is a quadratic. So I could use a quadratic or I could use a linear. I'm going to look at both. So I'll start with the linear. And when I look at that, it's not bad. I have an r squared that's 0.8. The r is 0.89. It's not too bad. When I look at the quadratic, I get an r squared of 1. It fits these points perfectly, just like the point principle said. So this is definitely the model that I'm going to use. But now that I have this, I can answer any question that they pose to me about this real-world data based on my model. So the question that I have is, what was milk production in the year 2000? Now, if I follow along this, here's the year 2000. So I'm going to try to dial that in. And it looks like milk production in 2000 was roughly 23.23 billion pounds. And I could do that for any year. I can look at what happened in 1970, get that dialed in a little bit there. I can look and see what happened back in 1955. It matches my data. But now let's talk about what happens when I go too far. So I'm going to zoom out on this a little bit and look what happened back in 1920. According to my model, they got 0 pounds of milk back in 1921. That doesn't make a whole lot of sense. And if I go back here in 1917, the United States was producing negative 2.81 billion pounds of milk. This doesn't make sense. Okay, so there's a reason for it. I want to look at this graph just a little differently because we're used to putting things in just like we see them, but you'll notice I really had to adjust my scale. Sometimes, and I'm going to use the same set of data, it makes more sense to take it out of year format. Okay, same numbers here, except I used 55 for 1955. I used 80 for 1980. This would be 2005. So if I'm looking for the year 2000 on this particular model, I'm looking 100 years. And notice I have the exact same answers. Realize you can do this, and this makes a lot of sense if we have a bunch of years close together. so I don't have to adjust these scales quite as much. But let's go back to this question of why is milk production in the negatives here, and somewhere down the road it's going to be in the negatives again. The other thing that we like to look at when we talk about these real-world models is extrapolation versus interpolation. Getting the model is easy enough. Once we get a handle of these different equations, we can come up with a model. But now we have to be able to interpret that, and sometimes they'll ask us questions about it. When we talk about extrapolating, this one can get dangerous. That means we're going to go outside our data points. So I have an example up here. I had plenty of points, but it looked like a cubic fit the best. And now that I have that cubic, extrapolating would be looking beyond what I have here. So maybe points to the left of 0, or some points to the right of that last data point. This can get us in trouble because if I'm looking at population or dollars or things like that, over here I'm going to get negative dollars. Or over here I might get this astronomically big number. Extrapolating you have to be careful with because things can get kind of big or kind of small and throw the whole thing out of whack. Interpolation is a little simpler. Interpolation means I'm going to stay within the confines of what I have for data points. So if they asked a question about this point right here, I could find that because it's within my data. Or maybe they asked me a question about some point over here, which is fine, it's inside my data points. But if all of a sudden they ask me about something out here, that would require extrapolation. It goes beyond what I have, and I need to be a little more careful with how I use this model.